Okay, go ahead and start. Did you already hit start? Okay. I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for the break, and I thank you again for these students. Pray to help us to understand a little bit more about the Jordan form and rational canonical form and all this stuff. This time we have today, Lord. In your name I pray. Amen. All right, so we try just to go over the big points of the extra magic hour lectures, which I wouldn't assume all of you have watched. I mean, some of you have, some of you haven't. It's okay if you haven't. Just you should be trying to watch those in the next few days. So basically, there are two major things we've come to. The one is the rational canonical form, and the other is the Jordan canonical form. And so basically, if we have a linear transformation from a finite dimensional vector space to another finite dimensional vector space over a field, right? And V is equal to, what is it? It's the, like this one, however many these are, S. Now this notation, like V, what this means is it's the set of f of t acting on V such that f of x is a polynomial over the field. It's the so-called subspace generated by V under the linear transformation T. And the elementary divisor theorem proves that there exists some set of vectors, V1 through Vs, whose direct sum, like this, build the whole space. And so the rational canonical form is kind of paired to this observation. So to each one of these, cyclic subspaces, as they're called, you can pair a very special kind of basis. All right, and that basis is formed by, like, how's it go? It's something like, it ends up being what? You can do this for a particular VJ. What's it look like? I'm trying to remember. I forget exactly. It's something like the span of, oh man, there's a, it's like the prime, the J, let's see, how's it go? PJ of T to the E minus, well, I guess it's EJ minus 1 V, and then you do T, PT, EJ minus 1 V, and then so forth, and eventually you get down to V. All right. I don't know. I went through it, and if you look at the matrix, of T, restricted to this thing, with respect to, sorry, awful notation. With respect to this basis here, which is a very special construction, let's call this beta sub j. If you look at the matrix of this with respect to the beta j basis, let's see here. What's the dimension of this thing here? It's trying to remember. I think it's the order of the polynomial p times the ej, if I remember right. So it's like dj, ej, or something like that. Anyway, this is a particular square matrix, and this is what's known as a is a companion matrix. You could say that this is the jth companion matrix in my current lingo. And I'll get in the details about what that looks like here in just a second. But long story short, that's what it looks like. Then if you make beta equal to beta 1 union beta 2, union all the way out, you do this for each one of these cyclic subspaces, then the total matrix is in the so-called rational canonical form, in the sense that it's blocks. It's like C1, C2, CS in my current lingo, and zeros elsewhere. And this is the so-called rational canonical form. Each one of these C's is called a companion matrix. It's the companion matrix. And this is a so-called rational canonical form. Let's see here if I can. It's probably better for me to focus on the parts here, as opposed to trying to give you a big picture example which does it all at once. If I do that, it will just get lost, and then we'll be out of time. So let me focus on the pieces here, which is just a little bit easier. Like, it could work out that P1, for example, P1 of x may be the elementary divisor, so-called elementary divisor corresponding to the cyclic subspace generated by V1, this guy. And suppose P1 of x actually looked like the following. I don't know. Let's say x squared plus x minus 3. Okay. So what would the companion matrix to this be? Well, I worked it out, right? I'm just going to kind of reiterate the result here, but it works out to 0, 1, 0, 0, 0, 1. So those are your ones below the diagonal, all right? And then in the last column, you have over here, what do we have? So I have to rewrite this. This is like x squared minus 1 times x, right? Minus 3. I mean, so what I have is minus 1, right? So I have minus 1 and then minus 3. Which comes first, the constant or the leading, next to leading term? The constant, right? So this goes minus 3 and then minus 1. Where this is coming from is studying this basis and actually expanding the matrix of the linear transformation with respect to this very specifically chosen basis. Like, this isn't just like falling from the sky. I actually derive where this is coming from if you watch all of the extra magic hour stuff. But it's with considerable work that we come to this understanding. Another example, if I had P2 of x, which could be, say, x squared plus x minus 3 quantity squared, well, that's going to give me a companion matrix C2, which looks like the following. It's going to look like, in his language, C1, C1, he calls this thing B in 0, where C1 is the one I have right above. So this is, if you have a repeated, like a squared one, it looks like this. And just to be more explicit, this is a what by what, oh goodness gracious, 6 by 6. So it's 0, 0, minus 3, 1, 0, minus 1, 0, 1, 0, 0, 0, minus 3, 1, 0, minus 1, 0, 1, 0. Zero's down here. Oh, it's calling me. Yes. Yeah? Okay. Okay, I'll call you back. Okay, bye. Sorry. Um, there's a birthday party today. We were planning. All right. Anyway, I mean, if you want to, I mean, you can. I can't stop you if you want to like get transportation over to the, what's it called? With the skating and the laser tag. Yeah, the Fun Quest. Yes. What's that? Is there a theme? I don't know if there's a theme. I'm personally very excited because my children have lost their obsession with Pokemon over break, and it gives me joy because I hate the Pokemon.
What is the replaced obsession?
Shaolin Showdown. So, did you guys know about the Shaolin Showdown? Shaolin Showdown? It's amazing. Yeah, I know, but it's on the Amazon Prime, and we are now in season 3. It is so much fun. Understanding where this one came from, it cost me about 2 hours of my life. I don't know. I just got really confused about understanding where this one came from. Well, that's why I do it for you. So I've accepted that I'm going to study my course more than any of you guys. I understand that. I've come to terms with that in my life. There might be an exception. I don't know. But but then I'll study again next year, so I will beat you. Don't worry. Unless you decide to start teaching the course, in that case I might have some competition. I don't know. But anyway, that's the companion matrix for a square. And this goes on. If you have a cube, if it was a cube, you'd put C1, 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 and then you've got a B1 here, and a 0 up there. And the story goes on. Anyway, the point is you can find a companion matrix to any possible like polynomial, right? There's always a companion matrix corresponding to a polynomial, which has, if it's not a square, if it's just just a plain polynomial, one's down the subdiagonal, and then the coefficients of the polynomial in the last column in the way I've described here. And because this elementary divisor theorem says that there exists this set of vectors, v1 through vs, for which what did we say? This P1 of x is called the what? This is called the order, right? This is the order of V1. If I recall correctly, we had the notation mv1 of x is equal to P1 of x, yeah? I believe. But I'm a little rusty. All right, so let me move on. So, this is super useful because it could be that you have something like this, which maybe I could factor that over the reals, actually. But certainly if I change that -3 to a +3, we're out of luck, right? Certainly if I put +3 there, we'd have complex roots, right? I think as it stands, it just has ugly real roots, which is also unpleasant, right? So, I mean, I don't think this can be factored over the rationals, can it? Would be my luck. Is that like, really? Is it, sorry, just humor me for a second here. No, okay, it's not what I was thinking. I was thinking 2 and 1, yeah, okay. It's, so if we're working over the rationals, the roots, we can't factor x squared plus x minus 3 unless we use irrational numbers, right? So if you're working over a rational vector space and you face this polynomial, you couldn't factor it because you don't have eigenvalues in the rational numbers for that. But in the case that we have eigenvalues, in the field for the linear transformation, things are much nicer. We have this thing called the Jordan form, which in some sense is a special case of the rational canonical form, but in another sense, it really kind of takes on its own life. I mean, let me try to explain to you what I was going to, which was the idea of chains. All right. So the context here is we're considering linear transformation from a vector space V to itself, okay? And all the characteristic values of T are found in the field. Right, so here, this is a vector space over a field, okay? For example, this would automatically be true if we were working with a complex vector space, right? Because every complex polynomial has how many complex roots up to multiplicity? I mean, including multiplicity? If I have a fifth order complex polynomial, how many complex zeros are there? There are 5, right? There's always as many as the power. When can you solve a quadratic complex equation? Always. And there's always 2 solutions, possibly repeated. All right? So that would be an example where this would be automatically true. But if you're working with something like the reals, it may or may not be true, right? You can have a linear transformation which does or which doesn't have all of its eigenvalues in the reals, right? So, but if it does, there's this wonderful theorem. So first of all, the characteristic polynomial of T, x, is going to look something like x. Oh, I've got to make a choice here, guys. Do you want me to do, if you don't mind, I'm going to be a double-minded man here and use both conventions at once. It's just nicer to write this for our current discussion, but computationally, I always flip it over. For specific examples, it's just easier to do the other way. But here, let me just go ahead and do this. So x minus lambda I to the m1 power, x minus lambda 2 to the m2 power, x minus lambda, let's say s, to the ms power, right? That's the first thing that happens. If all your eigenvalues are in the field, that means the characteristic polynomial can be factored into a product of linear factors possibly repeated. The multiplicities, m1 through ms, are referred to as the what? Are the algebraic multiplicities. All right. Now, what does the minimal polynomial look like in this case? So the minimal polynomial, again with respect to T, I seem to be inventing new notation today. Sorry, I hope you can forgive me. The minimal polynomial of T, we usually just been saying m of x in a lot of the extra magic hour stuff, but minimal polynomial of T with respect to x is then they're going to look like what? It's going to look like x minus lambda 1 to, let's say, n1, x minus lambda 2 to the n2 power, x minus lambda s to the ns power. Right? Now those don't have to be equal. The n's are what are called the geometric multiplicities. So n1, n2, ns are the so-called geometric multiplicities of the roots. I'm assuming what about the lambdas, by the way? Yes, but more than that. We're assuming they're distinct. Otherwise, my enumeration would be in vain. Okay. Okay, so there's in this lingo, right? Remember what we learned? We learned that if the what? If the minimal polynomial can be what? If it's, what did we have that theorem about diagonal before? What was it? What did we say about the minimal polynomial? Corresponds to diagonalizability. How? I mean, in our current language, if we have, oh no, I'm sorry. I've gotten turned around about the meaning of something. I don't think I should say those are geometric multiplicities. That's not right. I'm sorry, guys. I don't know what to call those, actually. No. These are not the geometric multiplicities. No, I don't know what these are. No. I mean, this much I can say. I know that n1 has to be less than or equal to m1, and n2 has to be less than or equal to m2, and so forth and so on. ns is less than or equal to ms, right? And I also know that in my current language, if n1 is equal to 1, and n2 is equal to 1, if all the n's, whatever they're called, are 1, then we have diagonable. That was our theorem before. If the minimal polynomial is just a product of linear factors, not repeated, distinct linear factors, then it's diagonalizable. That was the theorem we proved. So if we've got repeated linear factors here, if even one of these n's is, larger than 1, that signals, hey, this is not a diagonalizable transformation. What is that? In other words, there is not an eigenbasis for the transformation, right? So if we're going to construct a basis which puts T into some special form, we need something more than just eigenvectors, is my point. So what you do, all right, guys, is you look at these generalized eigenspaces. Generalized eigenspaces. Usual notation for these is something like this. K, like kj, let's say, is equal to the null space. Well, in my current language, kernel. The kernel of t minus lambda j raised to the m1 power. That would be the jth generalized eigenspace. If we have an eigenvector, not an eigenvector, if we have a vector, okay, so that t minus lambda j to the m1th power times x is equal to 0, and x is not equal to 0, then x is a generalized eigenvector of order m1. There's a theorem that's probably more or less a corollary to the things we've proved in Chapter 7. I won't prove the theorem for you. I'm just going to state it. But the theorem states this. It says V is exactly the direct sum of these k's. All right? So you can form V by the direct sum of these generalized eigenspaces. And then there's a very nice basis that you can construct for these generalized eigenspaces. And the now I've worked myself into a corner here. I mean, it could be. There's the possibility, guys, that these lambdas are over here at least, I could have two of these different k's corresponding to the same lambda. So there's something lost in what I'm saying. I'll show you with an example rather than trying to flesh it further out here. The point, though, is that how do you build one of these k's? What's the basis for it look like? Well, that's kind of the issue. I mean, this isn't wrong, but it's just not quite the Jordan form either, because for a specific eigenvalue, I want it to be like as nice a form as I can. So see, how can I explain this briefly? Probably best with an example. Show an example. All right, so if I had A equal to something like 3, 3, 3, 3, 3, and 2. All right, and I had a 1 here and a 1 here, but then zeros elsewhere. Then you see what I've got is I've got these blocks. These are so-called Jordan blocks. First of all, if the matrix is presented to you in this way, you can immediately read the eigenvalues off of it. All right? And let's see here. So check this out. So if I have A minus 3i times E2, what do I get? Let me make this more interesting, guys. Let me put a 1 here. Sorry. Forgive me. Regretting your decision to take notes in pen once more, huh? Let's see here. It's a mixed bag. A minus 3i times E2 is what? This is what? This is the column. So what does A minus 3i look like? So 0, 0, 0, 0, 0. So I've got yes, thank you. All right, so that's A minus 3i. So this is the second column, right? Of A minus 3i, which is exactly E1, right? What's A minus 3i times E1? 0, right? So if you look at this, once you have these two things together, this automatically tells you that E2 is a generalized eigenvector of order 2. Why is that? A minus 3i squared times E2 is what? That's A minus 3i times, well, what's the first A minus 3i gives you E1, right? And then that is 0. This is what I mean by a chain. So this makes E1 and E2 a chain of generalized eigenvectors belonging to lambda equals to 3 with length 2, right? Okay. What about E3, E4, and E5? What happens there? Well, A minus 3i times, let's see, 1, 2, 3, 4, 5. E5 is equal to E4. A minus 3I times E4 is equal to E3. A minus 3I times E3 is 0. Again, you can see those from multiplying over here. E5 is E4, E4 is E3, E3 is 0. Because that's columns 3, 4, and 5 there. This calculation I'm doing right now is probably more important, actually, than the theorem I was stating at the start. You really want to understand what's going on here. Now, what does this say? So if you look at this, then what is a minus 3i squared times E4 is what? That's 0, because if we plug in, that's really a minus 3i E3, which is 0, right? And then finally, this one gives me a minus 3i cubed, acting on E5 is equal to 0 for the similar reason, right? In other words, E5 is a generalized eigenvector, order 3. E4 is a generalized eigenvector, order 2. E3 is a generalized eigenvector, order 1. In other words, it's just a plain old garden variety eigenvector. You put these together, and you got a chain. E3, E4, E5 is chain of generalized eigenvectors of length 3 belonging to 2, 3. Okay. Now, the trouble with what I was trying to verbalize over here is I don't know if I can get any one of these k's, right, in my current lingo. Okay, the k's are just set up for distinct eigenvalues, right? There's no reason that one distinct eigenvalue can be one distinct eigenvalue's generalized eigenspace can be reached by a single chain. I may need multiple chains to cover each one of these generalized eigenspaces. Like the generalized eigenspace corresponding to eigenvalue 3 for this matrix A, right? Well, find the linear transformation corresponding to A, L sub A, if you like, would be how many dimensions I got here? It's almost all of R6, right? It's a hyperplane in R6 where the sixth component 0, right? That 5-dimensional subspace of R6 is the generalized eigenspace. Like here, if I'm enumerating my eigenvalues, lambda 1 equals to 3, lambda 2 is equal to 2, right? In my language over there, K1 would be what? The span of E1, E2, E3, E4, E5, and that's it. Whereas K2 would be the span of E6, which, by the way, would be the kernel of, well, find the null space in my current lingo, of A minus 2I, which is one-dimensional. So here's the theorem. The theorem is that you can always find a generalized eigenbasis for any transformation, provided that your characteristic values are in the field. In other words, you can always find these chains of generalized eigenvectors such that if you take them and you string them together, right, to make the total basis, this is called the generalized eigenbasis. And the matrix of the linear transformation with respect to a generalized eigenbasis will be in Jordan form. It'll have this block decomposition where each one of the blocks is a Jordan block. It's as close as you can get to diagonal when you can't diagonalize. And as I described in the extra magic hours, that also means that you can easily see how to decompose such a transformation into a diagonal piece plus a nilpotent piece. The diagonal piece is exactly the diagonal piece. In this case, it's literally 3, 3, 3, 3, 3, 2 in the diagonal plus this thing. This is the nilpotent piece. This is the n. and you have A is equal to that diagonal plus this nilpotent piece, and you can do all those things we talked about for transformations with this. So how do you actually find the Jordan form for a matrix? Well, it's a beast, right? Part of the reason I have not put this on an in-class test is because it's hard. Computationally, it's quite difficult. I don't think I'm really going to. I will not completely explain to you how to calculate it. I mean, I've showed you the existence of it by looking at those things we did, and well, I did in the extra magic hours. The actual computation of these things is involved. It's quite involved. I don't think it's really explained in your text either. So your text shines in certain ways better than other ones. Other texts do a better job of explaining how to find the Jordan basis, I will say that. Here's a sketch of what you do, though. What you got to do, first things first, you find your characteristic polynomial for the transformation, right? That's the first thing. You got to find what are the eigenvalues. Okay? If the eigenvalues are in the field, you can find a Jordan form. It's just a matter of persistence. The next thing you do is you factor. I guess I already said that. You factor the characteristic polynomial, right? You find the highest power, right? In this case, it would be this would have given you a characteristic polynomial with what? A minus 3i to the what? 1, 2, 3, 4, fifth power. Now, when you calculate a minus 3i to the fifth power, you know what you get? You get 0. That's right. And this is probably where the minimal polynomial comes into play, right? The minimal polynomial will be the highest non-trivial power, which is a non-trivial polynomial, and yet when you plug in a, you get 0. So I think when you look at a minus 3i cubed, you'll still get something non-zero. And so you'll be able to find something, you'll be able to find one thing which is a solution to a minus 3i cubed. That's your generalized eigenvector of order 3. That tells you pretty much that you're then going to find everything else either at level 2 or level 1. So, I mean, technically speaking, that's what you should do. You should start by finding the highest power of, the linear transformation minus the eigenvalue, which allows a non-trivial solution. That's your highest weight, your highest rank, your highest order generalized eigenvector, and you kind of just go from there, because once you have one of those generalized eigenvectors, how do you get ones below it? Like if I have that t minus lambda I to the k times v is equal to 0, where v is not equal to 0, what's that tell me? That tells me that I can look at t minus lambda I to the k minus 1, right, times t minus lambda I times v, and that will be equal to what? 0, right? But I can call this thing, let me call this v1. I can call this v2, right? Now, if that were 0, well, that would not be what I mean. V1 should be, this v1 is special, right? This is the first power k for which this happens, right? No smaller k. Okay, that's what I'm assuming here. It's like a first time it's 0, only for that kth power. If that's the case, then you know that this is non-zero, right? And you can see that that's a generalized eigenvector of order k minus 1. Because this times that gives you 0. And then you repeat this. If you split off, what would be v3? Lambda I squared times v1, right? And you can just keep doing this. Basically, once you have that highest power, the highest, the largest non-trivial generalized eigenvector, you just operate down, and you'll get a chain of length k from that. But then that might not be everything, right? You could have other things, and then you got to go look at the lower orders of t minus lambda I to find out how many eigenvectors do you have, and so forth and so on. So it's a complicated process to like find out how many chains there are and make sure you don't have them overlapping and junk like that. I'm mostly interested that you guys understand what this means and like just interpreting problems that are already put into either Jordan form or canonical form. That's primarily what I'm interested in you guys understanding as a first level of understanding, right? So how do you see minimal polynomials from the Jordan form? While we're on the topic. Oh, I'm sorry. One thing I should say before I get on with that. I mean, I just told you that. I mean, that's what I'm supposed to tell you, is you start with the highest thing and you go from there. Pragmatically speaking, what almost always works for me in examples is I first find the eigenvectors. Why make it more complicated than it needs to be? Find all the eigenvectors as a starting point. That's what I do, honestly. There's some malevolent example out there that will get you eventually, because logically you should really start the other direction and work your way down because of the structure. But honestly speaking, many examples, if you first exhaust the eigenvectors which are out there, right, that's a good starting point. If the transformation is diagonal, that's everything. You've got your eigenbasis, you're done, right? Otherwise, then you go looking for generalized eigenvectors of order 2 and higher. See if I can. What's the minimal polynomial? The minimal polynomial is easy. What you do is you look for the largest Jordan block of each eigenvalue. Here, the largest Jordan block is this 3 by 3. The largest Jordan block of the 2 is that. That means the minimal polynomial is x minus 3 quantity cubed times x minus 2. That will work because what it's going to do, when you plug in a, it's going to give you something up here which squares to 0 and leaves you something non-zero down here. Whereas when you plug in a into this, it will give you something non-zero up here, but 0 down here. When you multiply those two things, 0. So as long as you pick the largest Jordan block, it automatically, when you plug in the thing, will kill all the smaller Jordan blocks because they're already 0 when you multiply to that highest power. So that's it. That's the algorithm to find the minimal polynomial from the Jordan form. You just look at every Jordan block and find the largest block for each eigenvalue. That gives you one factor in the minimal polynomial. And that's how you do it. Okay, so let me see if I can actually work an example here. How about this? T equals 2. Now let's look at the let's look at differentiation, and let's look at our vector space being, I don't know, what is it? Oh, I'm sorry. I'm easily distracted. I don't want to make it too easy. It's no good. I need actually something with numbers. I have this malevolent example, but I'm not going to do it. It's confusing. It's confusing. Now, the reason we're doing what we're doing, guys, is once you guys understand how to find the Jordan form, what it looks like, the fact that it's always there for you in a real vector space, there's always a Jordan form. Now, that's not entirely true. That's a lie. It's a lie. But there's always a. It's always true except for when it's not. No, there's always something called the real Jordan form. That's what I'll explain to you guys next time. Oh, where's the example I need when I need it? Stink. I mean, the only example I can write off the top of my head is the one I've already shown you, which is dumb. I mean, it's not. Well, that's not that interesting. Oh, fine. All right. 0, minus 1, minus 1, minus 3, minus 1, minus 2, 7, 5, 6. Let's try to find the Jordan basis for that. We got 2 minutes. All right, so you guys are going to have to help me. What's the determinant of a minus lambda I? See, I've already, this is minus the characteristic polynomial technically. What is this? I regret my life. Golly. So obviously that's minus lambda times lambda. Why did I shut that book? See if you guys can figure it out faster than I can look it up. So minus 1 minus, you really should be using technology. I'd want you guys to use technology to do the numerical examples I've asked you in the quiz and stuff. I hope you're using technology to calculate these things. I really do, in as much as you can. What's that? So, okay, that's the main difficulty though, okay? The main difficulty is just finding that. Once I have that, then I can look for the eigenvalues, like so eigenvalue 1, so a minus I times, say, v1. What I'm looking for is a solution to what? Minus 1, minus 1, minus 1, minus 3, minus 2, minus 2, 7, 5, 5 equals to, that times, let's say, UVW equals to 0, 0, 0. I just subtracted 1 from the diagonal here. Oh man, this problem is really nasty. Curses. And then a minus 2I v2, what's that? I blame Lorenzo. Just kidding. UVW are my disposable variables. So I need to solve. You find solutions to these. Man. These are happy. Get out of here. Leave me. I will try to work an actual example next time as numbers. Uh-oh, I knew something was up.